By popular request, I hereby provide this video explanation for the questions offered or given in quiz 8. So the first question asks about the Lewis structure of N2H2. What does that look like? Well, let's go here to the dot cam. So we'll go through the steps of drawing out a Lewis structure. Drawing a Lewis structure involves a series of steps. Step 1 is write down the number of total valence electrons you have in the entire molecule. Now, nitrogen is in column 5A of the periodic table, therefore nitrogen has 5 electrons, okay? There are 2 nitrogens in this formula, so I'll times that by 2. Hydrogen's in column 1A of the periodic table, so there's 1 valence electron in the hydrogen. And there are 2 hydrogens in this formula, so I add that all together, I get 10 plus 2 equals 12 total electrons to play with in this system. That's the end of step 1. Now remember, what I'm talking about here are valence electrons. I'm not talking total electrons, just valence electrons. And that corresponds to the column, the A column, be it 1A, 2A, 3A, 4A, and so forth, in which that element appears on the periodic table that I'm not showing here. Okay, the next step is you start by writing down the least electronegative element, which most of the time is the element that appears furthest to the left in the formula, in this case nitrogen, in the middle. In this case, however, we have 2 nitrogens, so I'm going to just draw 2 nitrogens, and you link them together with bonds. Now, the one exception in this rule is hydrogen. You never, ever, ever, ever put hydrogen in the middle, even if it is the least electronegative element in your compound, because hydrogen can only attain 1 bond. Unlike all of the other elements except helium, hydrogen only wants a 2-tet, not an octet, so it can only form 1 bond. So I start out by writing out my, in this case, 2 central atoms in the middle, and I put a bond between them. Now I've got 2 hydrogens, so I'm just going to add them around the perimeter, okay? All right, so what I've written down here is 2, 4, 6 total electrons. Remember, each line represents 2 electrons, so I've already put down 6 total electrons. So the next step is using your remaining electrons, put them down as lone pairs around all of the atoms that are furthest out from the middle until their octets are fulfilled. Now in this case, hydrogen already doesn't want an octet, it just wants a 2-tet. So this hydrogen, its 2-tet is already fulfilled because it's experiencing 2 electrons in that bond, okay? That hydrogen has a 2-tet, so does this one. So we're done with that step. So the next step is start putting down lone pairs on your central atoms until their octets are fulfilled, or you run out of electrons. Now remember, we've used up 2, 4, 6 electrons of our total 12. So how many electrons do I have left? Well, I have 12 minus 6 left, which is 6. So I'm going to start putting them down. So I'm going to start putting them down as lone pairs on these atoms. So I'll go ahead and put down 1, 2, 3, and 4. And now that nitrogen's octet is fulfilled because it has a bond to the left, bond to the right, lone pair, that's 2, 4, 6, 8. Now I have 2 more electrons in my count that I can put on this nitrogen. So I would like to, I'm sure, put another lone pair on this nitrogen, but I can't because I only have 12 electrons in the system and I've used them up. I've used them up, so I've got 2, 4, 6, 8, 10, 12. So I can't just magically conjure another pair of electrons somewhere. I don't have any. You'll also notice then, as we look at this, that this nitrogen here feels like it has a full octet because it has 2, 4, 6, 8 electrons surrounding it. This nitrogen, however, does not. It only has 2, 4, 6. So what do I do here? Well, this is where we have the last step, which we don't always do, but the last step is, wherever necessary, form multiple bonds. How do you form a multiple bond? Well, you put a circle around one of the lone pairs, and then you push it like a bowel movement down into or between 2 atoms, and when it falls in there, it goes plop, and it turns into a bond. So I'm going to grab this lone pair, I'm going to push it down like a bowel movement, and when it flows in there, it turns into a bond. So I'll now redraw what that just made. See that? That made this molecule right here. Now you'll notice as we do the full count that I still only have 12 electrons in the system. I have 2, 4 in this lone pair, 6, 8, 2 per bond, 10, 12. So I have not violated the 12 count that I have here. But you'll also notice that by forming that double bond, each nitrogen now feels like it has 8 electrons surrounding it. It has a bond to the left, and this one has 2 bonds to the right, and a lone pair. That's 2, 4, 6, 8. The nitrogen over here to the right has 2 bonds to its left, 1 bond to the right, 2, 4, 6, and a lone pair is 8. So everyone's octet is fulfilled. So that is a correct Lewis structure for this molecule N2H2. So if you look at the multiple choice lineup, what of these would be correct? Well, it's option C. Each nitrogen has 1 non-bonding electron pair. What is a non-bonding electron pair? it's another word for a lone pair. So that nitrogen right there has one non-bonding electron pair or a lone pair, and so does that one. So option C is correct. Let's see if any of these others are correct. So option A says that nitrogen-nitrogen triple bond is found. Not true. We have a nitrogen-nitrogen double bond. Nitrogen-nitrogen single bond, not true. Each nitrogen has two non-bonding electron pairs, or in other words, two lone pairs, no. And each hydrogen has one non-bonding electron pair, not true. Only C is true. Each nitrogen has one non-bonding electron pair. So we're done with question 1. Now let's go to question 2. There are blank valence electrons in the Lewis structure here, okay? So let's go ahead and take this formula. We'll go back to our dot chem and I'll write it down. Okay, so I'm going to go ahead and write down CH3, CH2, Cl, okay? How many valence electrons are there in this molecule? Well, if you look at carbon on the periodic table, it's in column 4A, therefore it has 4 electrons, or 4 valence electrons. It actually has more than 4 electrons if you're counting core electrons, but remember, this is valence electrons, which corresponds to the A column that element appears in the periodic table. The one exception is D electrons that have kind of weird rules I won't bog you down with, okay? Hydrogen's in column 1A, so it has 1 valence electron, and this formula has 3 hydrogens at this position, okay? This carbon is another carbon here, so I'm going to add that to the mix. It has 4 valence electrons, and then each of these hydrogens, like the other hydrogens, have 1 electron per hydrogen, and there are 2 total hydrogens, okay? And I'm going to add all this together. And then chlorine. Chlorine, if you look on the periodic table, has 7 valence electrons, so I'm going to add 7 to it. So those are all my valence electrons. I have to just do the math now. So I've got 3 times 1 is 3, plus 4 is 7, plus another 4 is 11, plus 1 times 2, that's 2, plus 11 is 13, plus 7 is 20. So the answer to this question is 20 total valence electrons. So that is what this question is asking. How many valence electrons do we see total in this structure? The answer is 20, which lines up with option D. Now let's go down to the Lewis symbol for a sulfur atom. Now Lewis symbols are a little bit different from Lewis structures. In Lewis structures, like the one we did, for example, up here with this N2H2, when we put electrons on an atom, we do pair them up. We do not put like one electron on one side of an atom and another by itself on the other side of the atom. You do not do that in Lewis structures. You pair them up. In Lewis symbols, however, you do not pair them up until you have to, okay? So Lewis symbol is a single atom written down with its lone pairs surrounding it. If you look at sulfur on the periodic table, it appears in column 6A, which means it has 6 valence electrons. So I'm going to draw 6 dots around it. 1, 2, 3, 4. I pretend that the sulfur is kind of inside a box or a square. And each side of the square can hold up to 2 electrons. And remember, I do not pair them until I have to. So I've got 1, 2, 3, 4. But there's 6 valence electrons in the sulfur, so I'll have to pair up some electrons here. So I'll go 5 and 6. So there's our Lewis symbol for sulfur. It has two pairs, I guess, and then 2 electrons that are not paired, okay? So with that said, in the Lewis symbol for sulfur atom, there are how many paired electrons and how many unpaired electrons? Well, there are 2 pairs of electrons, but how many electrons total of paired electrons does that consist of? Yeah, it's 4. I've got 1 electron here, 1 electron here, 1 electron here, and 1 electron here. That's 4 total electrons that are all in the pairs. So how many total electrons are paired? There are 4. How many unpaired electrons are there? There are 2. So the Lewis symbol for sulfur has 4 paired electrons and 2 unpaired electrons, which lines up with option B. Now let's go down to nitrite, and this is talking about something that we'll have to draw out a Lewis symbol in order to get right. So nitrite, NO2 minus. Okay, so I'm going to scroll down here and we'll write down NO2 minus. NO2 minus drawing its Lewis structure, which is what we really need to do in order to answer this question. We go through the same steps as before. I'm going to get my valence electron count. Nitrogen's in column 5A of the periodic table, so I write down 5 electrons there. Oxygen's in column 6A, but in this particular molecule, we have 2 oxygens, so we have to multiply that by 2. And for charges, you also have to add that to the account. For negative charges, you add 1 electron per negative. For positive, you take away 1 electron per positive. This is a negative charge, so I'm going to add 1. So I multiply and add all this together. 6 times 2 is 12, plus 5 is 17, plus 1 is 18 total electrons. So I have 18 valence electrons in the count. Now let's draw out our Lewis structure. Remember, the next step is we start by writing out our least electronegative element. In the middle, we have nitrogen and oxygen. Nitrogen is further to the left on the periodic table, so it's less electronegative. So I put that in the middle, and I draw a single bond out to the other atoms. In this case, there's only 2 other atoms. They're oxygens, okay? I've now laid down 2 4 electrons. 4 electrons in my total count of 18, so I have 14 left. The next step in the Lewis structure approach is we need to put down lone pairs on the exterior atoms. That is the atoms that are all around the perimeter until I fulfill their octets or run out. Okay? So I've used up 2 4 electrons. I've got 14 left. So let's go here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used up 12 of my 14. The next step is if you still have electrons left, then you put them on the central atom, even if doing so violates its octet. In this case, this central atom needs an octet, so we'll go ahead and put down 2 electrons there. So you'll notice looking at this structure here, I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18 total electrons. Now, strictly speaking, when you're dealing with Lewis structures for charged substances, you're supposed to write brackets around the molecule with a little charge floating in the upper right. Or it's also acceptable to write a shorthand. And shorthand is where you just put sort of the upper right-hand section of a bracket like that. So that's another acceptable way. Now, one thing that you'll notice looking at this is that the central atom does not have a full octet. That nitrogen only feels like it has 2 electrons to the left, 2 to the right, and 2 up top, 2, 4, 6. So how do I fulfill its octet? Well, to fulfill its octet, I have to form multiple bonds, and this is where we come to the last step. The last step is not always necessary, but it is whenever you're in a situation where we have an atom that does not fulfill its octet. So how do I form a multiple bond? I grab a lone pair on an adjacent atom and treat it like a bowel movement. So I'm going to push it, and when I push it, it goes, and it goes plop, and it falls down there. When it falls down there, it turns into a multiple bond. So now we'll redraw, and this is now the new Lewis structure that was formed. Does that make sense? Now you might ask, Mike, couldn't you have grabbed one of the lone pairs on the oxygen to the right and done the same thing? Well, yeah, if I did that, I would end up with this structure down here. Oh, and I forgot to draw my charge. But anyway, you see what I'm saying? So if I grabbed a lone pair on the oxygen to the right, push it down to form a double bond, I'd have the structure on the right. Now, what do you notice about these two structures? They're actually exactly the same. Now, I know that you might think, no, wait a minute, they're not the same. The oxygen here has a double bond on the right and a single bond on the left, and it's the opposite over here, but guess what? Take this molecule, and if you understand that oxygen atoms, an oxygen atom is an oxygen atom is an oxygen atom. These are chemically identical oxygens. So if you put your hand underneath this molecule, picked it up, scooped it up like a pancake, flipped it over left to right, and laid it back down on the page, it would look exactly the same as the molecule here to the left, or here on the right. See what I'm saying? Just pick this thing up like a pancake, flip it over, lay it back down, they look exactly the same. I'm telling you that these two molecules are equal. Now, what does that really mean? What it means is that in reality, this double bond is actually flipping out and turning back into a lone pair on this oxygen, while this lone pair flips back in, turns into a double bond, and then it circulates back and forth and back and forth. So if you can kind of picture that, picture this electron laying down here, turning into a double bond, and then this set of electrons doing the reverse. It lays down here like double bond, then pushes like dominoes this thing back up onto this oxygen, turns back into a lone pair. Then that lone pair pushes back down, turns back into a double bond, and pushes this double bond back up onto this oxygen, turns it back onto the lone pair. If that's going like at an infinite speed, as atoms do, or roughly infinite by our imaginations at least, then what that really means is that both of these bonds in net end up being not a pure double bond, not a pure single bond, but somewhere exactly in the middle. So each of them is like somewhere between a single and a double bond. I'll call it a 1.5 bond. So what does that really mean? It means that the oxygen-nitrogen bonds are actually identical chemically. They have the exact same length and properties. So which of these is true? Option A says that both bonds are single bonds. That's not true. And I don't know which both bonds it's talking about. I guess the bonds between the nitrogens and the oxygens. B says both bonds are double bonds. Also not true. Option C says one bond is a double and the other is a single. That is one thing that you'd think would be true based on the drawings, but remember that real-life molecules, their electrons are constantly moving and in flux. So this is just a snapshot of what this molecule looks like in one moment, and then this is a snapshot of the other. In reality, the bond between the nitrogen and oxygen are actually halfway in between the double and single because it's fluxing continually. Okay, so option E says there are 20 valence electrons, and that isn't true. There's only 18, so we can cross that off. So both bonds are the same. That is actually true. So the option is, or the answer is D. Now I'll go here to option or question 5. It says a valid Lewis structure of blue cannot be drawn without violating the octet rule. Now, in order to do this, as tedious as it is, we really have to draw out all of the Lewis structures for this, unless you have the ability to see it really quickly. But let's go ahead and start with the first one, NF3. Okay, so we're going to go ahead and draw our NF3. I start by writing out the valence electrons. Okay, so nitrogen's in column 5A, so it's 5 electrons. That's a 5, not an S. F is in column 7A, so there's 7 valence electrons per F, and there's 3 total Fs. So I'm going to do 7 times 3 is 21, plus 5 is 26 total electrons to play with. I lay down the least electronegative atom in the middle, and then I put bonds out to all the perimeter electrons. Okay, I've used up 2, 4, 6. I have 20 electrons left. I now lay them down as lone pairs on each of the perimeter atoms, that is the atoms on the outside, the fluorines in this case, until I fulfill their octets or run out of electrons. So each fluorine has one bond, feels like 2 electrons. Now I have to add 3 lone pairs to complete its octet. 1, 2, 3, 4, 5, 6. That fluorine's good. 1, 2, 3, 4, 5, 6. That fluorine's good. 1, 2, 3, 4, 5, 6. That fluorine's good. So I've now used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, or 22, 24 total electrons. I have 2 more electrons to get up to 26. What do I do there? Well, that's the next step. If you have leftover electrons, you put them as lone pairs on the central atom, even if doing so violates the octet. So that is a full thing, and you'll see that this nitrogen now has a full octet. Has 2 electrons to its left, 2 to the right, 2 downtown, and a lone pair up top. So everyone's octet is fulfilled. That is a beautiful Lewis structure for that molecule. This question says, which of these following molecules cannot be drawn without violating the octet? You can see clearly that is not option A. So let's skip down to option C, which is PF3. One thing you'll notice about PF3 is that phosphorus happens to be in the same column of the periodic table as nitrogen, so it has 5 valence electrons as well. Fluorine is, so what I'm telling you is that the Lewis structure for this thing is going to be basically exactly the same as the one we just drew, except the phosphorus will be in the middle. So I'm going to be kind of fast here, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So that's the Lewis structure of PF3, phosphorus trifluoride. It also has a complete full octet with 26 electrons, so the answer is not C. Now we'll go to antimonium fluoride, so antimonium trifluoride. So antimonium, if you look at it on the periodic table, also is in the same column. So what I'm telling you is it has 5 valence electrons, just the same as nitrogen and phosphorus. Fluorine still has its 7. So if you go through the whole gamut that I just did, you end up seeing that the Lewis structure for this compound, antimonium trifluoride, is exactly the same as the others that we just dealt with, except you swap out the middle element, be it phosphorus or nitrogen from earlier, with an antimony. And that is the Lewis structure. Full octet, everything looks beautiful. And option E we'll battle with here for a second. But one thing that you can kind of notice is this kind of question is really a question that is one of these is not like the others. That's really what this question is. One of these is not like the others. You'll notice that all of these structures, A, C, and D, look exactly the same except for the first element, be it nitrogen, phosphorus, or antimony. And if you look at the periodic table, you'll notice that those elements, nitrogen, phosphorus, and antimony, are all in the same exact column as each other. So what I'm telling you is that A, C, and D are like each other, right? And this question is really asking one of these is not like the others. So you can kind of cross out by that logic without drawing out a full Lewis structure for all of them, A, C, and D. But what about E, sulfate? Well, sulfate's a little bit trickier, I suppose, but we go through the same steps. So sulfate, SO4, 2-. Sulfur is in column 6A of the periodic table. Oxygen is also in column 6A. There are 4 oxygens in this formula, and I have 2 additional electrons here embedded in that 2- charge. So 6 times 4 is 24, plus 6 is 30, and add 2, I've got 32 electrons, okay? I put down the least electronegative atom in the middle, which is sulfur, and then I put out 1 bond to all of the other atoms. Okay, those are these oxygens here. Now I'm going to start adding lone pairs on all the other, the perimeter atoms, the atoms around the periphery, until I fulfill their octets or run out of electrons. And I think I have plenty of electrons here in 32, so I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And you'll notice that if I count the electrons in the bonds, I've got 26, 28, 30, 32. So let's do this again here. So again, I just want to double check everything. The bonds count as 2 per bond. 2, 4, 6, 8. Then up here I got 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that uses up my 32 electrons, and you'll notice that everyone has a full octet. All the oxygens have full octets. So does the sulfur, because it's got 4 bonds around it, which is 2 electrons apiece. Everyone has a full octet. So sulfate also has a Lewis structure that does not violate the octet rule, so it's not the correct answer. So let's go to IF3. What does IF3 look like? Well, let's write down the formula, IF3. Now, iodine is in column 7A of the periodic table, so it has 7 valence electrons, and so is fluorine. So we've got 7 valence electrons per fluorine. 3 fluorines total, so I have 7 times 3 plus 7 is 21, plus 7 is 28 total electrons to play with. I put the least electronegative element in the middle, which is most of the time the element that's written leftmost in the formula, the exception always being hydrogen. And then I put a single bond out to the other elements in the formula. So I've got iodine bonded with 3 fluorines. I've used up 2, 4, 6 of my electrons. I have 22 electrons left. So I'm going to start laying them down as lone pairs on all the fluorines until I fulfill their octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Everyone's octet is fulfilled. So again, let's count up all the electrons we've used here. I've got 2, 4, 6 in these bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 4 more electrons to get to 28. What do I do with those? Well, the next step is lay them down on your central atom, even if doing so violates your octets, right? I didn't mean to write that extra line there. So what I'm saying is you're going to have to lay down a lone pair on the iodine, and if I lay down that lone pair and do a full count, I've only used 26 electrons. I have 2 more electrons to play with. So what do I do? Yeah, I have to lay down another lone pair on the iodine. So as weird as this sounds, and I don't really know how else to draw it, this iodine's actually going to have 2 lone pairs. 2 lone pairs on it. And sometimes you'll see like people write things like this that represent sort of lobes of orbitals containing those lone pairs coming off of the iodine. You don't really have to do that. I'm just going to lay them down as 2 lone pairs, but you can see that that iodine has a hyperoctet that's more than 8 electrons. Now, is it possible to do that? The answer is yes. As it turns out, once you get down to row 3 and below of the periodic table, atoms can have hyperoctets, that is more than an octet on them. And the reason is because they have d orbitals into which extra electrons can go. And that's true even for elements in row 3 that don't have any d electrons in their electron configurations. They still do have empty d orbitals out there in the ether into which they can add more than 8 electrons. So that violates the octet rule because the central atom has a hyperoctet, it has 10 electrons around it, which makes option B this question's correct answer.